Hadoop MapReduce 2.0 version. Content of this lecture: in this lecture we will discuss MapReduce paradigm and also what is new in MapReduce version 2. We will also look into the internal working and the implementation overview. We will also see many examples how using MapReduce we can design different applications and also look into how the scheduling and the fault tolerance is now being supported inside the MapReduce implementation of version 2. Introduction of MapReduce, we have to say that MapReduce is a programming model and associated implementation for processing and generating the large data set. Now, in version 2.0, MapReduce version 2.0, now we have separated out the programming model, and as far as the resource management and scheduling is done using YARN, which is another component of Hadoop 2.0. So, in Hadoop 2.0, if we see this kind of a stack, so it becomes 3 different layers. So, the first layer is HDFS 2.0, then this is Hadoop 2.0, and then comes the YARN, and here the MapReduce version 2.0. So, now YARN will do the functionalities of resource management and scheduling, which was a part of MapReduce 1.0 version. So, this will make the simplification into the MapReduce, which is only now the programming model. It will focus on the programming aspect, and rest of this particular part, that is the resource management and the scheduling, will be performed by YARN. So, with this we can design many new application on this particular HDFS and YARN bypassing the MapReduce also. So, we will see the Hadoop stack or different distributions which either uses HDFS YARN or HDFS YARN MapReduce, or top of it lot of applications are available for big data computations. Now, in this particular framework, that is MapReduce version 2, which is now purely a programming model, the users can specify the map function that processes a key value pair to generate a set of intermediate key value pairs, meaning to say that the map function it is accepting the input in the form of a key value pair, which is quite trivial. Why? Because any data set we can represent in the form of a key value pair. So, the records is nothing but a key value pair. So, this will become the input to the map function, and output is also the specified in the key value pair. So, what is the key and value pair, that we will discuss in more detail in the further slides, but let us understand, let us assume at this point of time that any set of records or a big data set we can represent easily in the form of a key value pair. It is not a big thing that we are going to discuss. Then the second part is called the reduce function. So, reduce function merges all the intermediate values associated with the same intermediate key. So, that means the intermediate values or the output which is generated by the map will be the input to the reduce function, that is the output of map function, that is nothing but in the form of a key value pair, that is in the intermediate form of the result, and then it will now do the combination, it will combine it and give the final output. It will combine and combine by the key and give the results out. So, the map function and reduce together will perform in parallel all the computations which are desired to process the large data set. And so many real world applications or the task we can express using this particular model, that is using MapReduce jobs. So, this particular model allows to execute the application in parallel at all the machines which are basically running the task, that is the slave machines. So, the programs are written in this style are automatically executed in parallel on a large cluster of commodity machines. So, the parallel programming paradigm is automatically being taken care, and the users or the programmers are not going to be bothered about how the parallelization and how the synchronization is to be managed. So, parallel execution is automatically done in the MapReduce framework. Now, as far as the runtime is concerned, runtime take care of the details of partitioning the data, scheduling the program's execution across the set of machines, handling machine failures, managing the required inter-machine communication, and this allows the programmer without any experience with the parallel and distributed computing to easily utilize the resources of the large distributed system. So, let us explain this entire notion of a runtime operations which this particular MapReduce allows or provides to the execution environment to the for the execution of these programs on a large scale commodity machines. So, as far as MapReduce is concerned, now starting with the data set, the input data set, we assume to be a very large and is stored on the clusters. That means, may be stored on hundreds and thousands of nodes, one data set, let us assume that it is stored. So, this will be stored with the help of the partitioning. So, the data set will be partitioned and stored on these nodes. So, let us say that if 100 nodes are available, the entire data set is partitioned into 100 different chunks and stored in this way for computation in this scenario. Now, the next task is to schedule the program's execution across these, let us say 100 different machines where the entire data set is stored. So, then it launches the programs in the form of a map and reduce will execute in parallel at all places, that is, let us say if 100 different nodes are involved, all 100 different chunks will experience the execution in parallel. So, this is also to be done automatically by the MapReduce using the job tracker and the task tracker that we have already seen. And in the newer version, that is 2.0, this particular scheduling and resource allocation, this is to be done by the yarn. Once this particular request comes from this MapReduce execution for that particular job of that data set. Now, there is a issues like these nodes are comprises of commodity hardware that we have seen in the previous lecture of HDFS. So, the nodes may fail. In case of node failures, automatically it will be taken care by doing the scheduling of this alternative replicas, and the execution still carries on without any effect on the execution. So, it requires also to manage the inter-machine communications. For example, the intermediate results, when it is available, then they are sometimes required to communicate with each other some values, some results. This is called shuffle and combine. So, shuffle and combine requires inter-machine communication, that we will see in more detail in the further slides. Now, this will allow the programmers without any experience with a parallel and distributed systems to use it, and this will simplify the entire programming paradigm, and the programmers has to only write down a simple MapReduce programs. So, we will see how the programmers will be able to write the MapReduce program for different application, and the execution will be automatically taken care by this framework. So, a typical MapReduce computation may vary from terabytes on thousands of the machines. So, that we have already seen. Hundreds of MapReduce programs have been implemented, and upwards of 1000 MapReduce jobs are executed on Google's cluster every day. So, the companies like Google and other big companies which works in the big data computation, they uses this technology, which is the MapReduce programs. That means applications are written in the MapReduce, that we are going to see them. Now, we will see these components which are used in the MapReduce program execution, and they are the chunk servers, where the file is split into the chunks of 64 megabytes, and these chunks are also replicated. This is also sometimes called as a blocks, we call it as chunks. Both are synonymous to be used here in this part of the discussion. Now, another thing is these particular chunks are replicated, sometimes 2 times replication or 3 times. This is called replication factor. So, it is replicated, that means every chunk is stored on more than one, that is more than one nodes. For example, when it is the replication factor is 3 times. So, every chunk is stored on 3 different nodes. Sometimes they are tried to be stored on a different rack to have the rack failure tolerant. So, that means if the node on one rack, or if one rack fails, so it continues to get the other replica on a different rack. So, that is how different replications are done to support the fault tolerance or the failure tolerant. Now, the next component of a distributed file system, which is used here in the MapReduce, is called master node, also known as the name node in SDFS, which stores the metadata. Metadata means the information where the exact data is stored on which data nodes. So, this information is maintained at the master node by, and it is also called as a name node in the terminology of SDFS. Now, another component is called client library for the file access, which talks to the master to find out the chunk servers, connect directly to the chunk server to access the data. Now, we will see about this MapReduce and its motivation, why we are so much enthusiastic about this MapReduce programming paradigm, and which is very much used in the big data computation. So, the motivation for MapReduce is to support the large scale data processing. So, if you want to run the program on thousands of CPUs, and then this MapReduce is the only paradigm available, and all the companies which are looking for the scale, large scale data processing, the MapReduce is the only framework which is basically doing all this task. Another important motivation is that This particular paradigm makes the programming very simple and does not require the programmer to go and manage the intricacies of the minute detail underneath. Now, MapReduce architecture also provides automatic parallelization and the distribution of data and the computation of it. So, the parallel computation on distributed system is all abstracted and the programmer is provided a simple MapReduce paradigm, and he does not have to bother on these details. Automatically the parallelization and distributed computation is being performed. Another important part is the failures. So, the fault tolerance is also supported in the MapReduce architecture, and the programmer does not have to bother about that. Automatically it has taken care, provided the programmer gives sufficient configuration information, so that this fault tolerance is taken care of in different applications. Another thing is input output scheduling is automatically done, so that a lot of optimizations are used to reduce the number of I/O operations and also improve upon the performance of the execution engines. So, that is all automatically done by the MapReduce architecture. Similarly, the monitoring of all the data nodes, that is the task trackers execution and their status updates is all done using the client server interaction in the MapReduce architecture, that is also taken care of. Now, let us go in more detail of the MapReduce paradigm. So, let us see what this MapReduce is from programmers perspective. This particular map and reduce terms is borrowed from the functional programming language, which let us say that Lisp is one such programming language which has this kind of features, that is MapReduce. So, let us see the functionality which is supported in the functional programming language of MapReduce, and let us say that we want to write a program for calculating the sum of squares of a given list. So, let us assume that the list which we are given is 1, 2, 3, 4 is a list of numbers, and we want to find out the squares of these numbers. So, there is a function which is called a square, and a map says that this particular square function is to be applied on each and every element of the list. So, let us see the output will be that for that means the element number 1 when the square is taken, 1 will be there, 2 square is 4, 3 square is 9, 4 square is 16. So, all the squares are computed and output is given again in the form of a list. Now, this particular operation is square may be executed in parallel at all the elements, and this result will be given very efficiently. It is not that sequentially one by one all the squares are being computed. So, therefore, it will process them independently instead of these records are not to be carried out in sequentially, hence it is a parallel execution environment of map function that is performing the square operation on all the elements which are being provided in the map function. Similarly, to find out the sum, this was to calculate the squares. Now, another routine which is required to make the summation of this intermediate result. So, this result is called intermediate result. So, with this input we have to perform another operation which is called a reduce. Reduce will require an addition operation, the addition on this particular list, which is nothing but an intermediate result which is calculated by the map function. And you can see that the sum is the binary operator. So, it will start doing the summation 2 element at a time, and once they are calculated, so the entire output will be given in the form of whatever is required, sum of the squares. So, this is the sum of squares. So, given this kind of functionality or functions of a functional programming language, we will see that how this particular MapReduce can be applied here in the Hadoop scenario. Now, let us see a small application, simple application, or here it is written as sample application of a word count. So, that means let us say we have a large collection of documents. Let us assume it is a Wikipedia dump of particular Shakespeare's works. It can be any different important persons related works. We are going to process this huge data set, and we are asked to find out to list the count for each of the words in this one document, and then query will be to find out a particular reference in the Shakespeare's works about the characters, which character is more important based on how much referencing Shakespeare has done for that character. So, let us see how this is all done using MapReduce. So, MapReduce will huge collection of data set. First, it will be considered in the form of the key value pairs. For example, if it is the document is, let us say, welcome everyone, hello everyone. So, here this is the key is about every word is becomes a key, and how many times it is appearing in a particular sentence is becomes the value. So, the file is also given the input in the form of the file name and the text and the file text. So, so this becomes the key value. So, file name will be the key, and these text becomes the value. And further on, when we process using map function, when we apply a map function on this particular input, it will generate this another intermediate key value. This is called intermediate result in a form of a key value. So, that means for every word will become a key, every word will become a key, words will become a key, and the instances when it is occurring into a particular line of a file, then it becomes the value. For example, in a line number 1 welcome is appearing once, so it gives 1. Similarly, in the line number 1 everyone is also is available only once. Similarly, in the second line when it is being processed, so hello is appearing once, so it will be treated as once, and on the second line everyone is appearing again. So, this particular key value which is emitted out of map is further used by the reduce function. Now, let us say that let us see how in parallel this map function can work. For example, these two lines instead of process them sequentially, let us divide into two different chunks, and this chunk will be given a map function 1, and this another chunk will be given second map function. So, if there are two chunks, we are going to process them in parallel. So, this particular task map task 1 will execute, and map task 2 will also execute in parallel. So, in parallel if they are executed, so this key value pair welcome and everyone will be collected up by the task number 1. Similarly, the other task, that is hello and everyone, will be collected in the map task 2. So, we need to say that this particular map function allows the process individual record to generate the intermediate key value pairs in parallel, and that is done automatically. So, parallelly process a large number of individual record to generate the intermediate key value pair that we have seen if these numbers or the chunks are increased more than 2, then this is an example where multiple map functions are simultaneously at the same time, that is in parallel they will execute and process these records. Now, we will see the next phase, that is called reduce operation. So, after the map, the intermediate values which is being generated in the form of a key value pair will be used as the input for the reduce function. So, reduce processes these intermediate values which is output by the map function, and then merges all the intermediate values associated per key. That means, based on the similarity of the key values, they are all combined together, that is group by key operation is being performed. And using in this particular group by key operation, whatever is the reduce function applies, this will be the computation will come from the reduce function. So, computation on this group by key will be applied by the reduce function to get the entire output. For example, if this is the input which is input to the reduce function and we want to do a word count. So, now what it will do is it will group by the key. When you say group by the key, then everyone is appearing twice. So, with everyone there are 2 different values, or 2 times this everyone, one will come and this will be added up by the reduce function. Similarly, hello one is appearing once. So, group by key is having only this tuple or entity, similarly for welcome. So, this particular reduce function will execute in this particular manner. So, each key assigned to one reduce function, and here we can say that if there are 2 different nodes which runs this reduce task, let us say reduce task 1 and reduce task 2. So, each key is assigned to one reduce task. For example, this particular key will be assigned to the task 1. So, when this second key also second time when everyone comes, it should also assign to that same reduce task, whereas welcome and hello can be assigned to the reduce task 2. Now, parallelly process and merges all the intermediate value by partitioning keys, that we have already told you, but how these keys are to be partitioned, and a simple example is let us say that use a hash partitioning. That means, if you have a hashing function f, and when you apply this hashing function on a particular keyword, it will give a particular value, and this value will be mod how many number of reduced tasks. Here let us assume that it is the number of tasks is 2 and modulo some hash function, and on that particular hash function we have to define a key, and this will generate the partitioning. So, partitioning we have shown you through a simple example the way partitioning is carried out, that is through the hash partitioning. It can be very complicated also, depending upon different application how the partitioning is done and how many different worker nodes or reduced nodes are there, or reduced task is allocated by the yarn, and based on that this particular partitioning is done, and after partitioning then it will merge the intermediate values and gives the result back. Programming model. The computation takes a set of input key value pairs and produces a set of output key value pairs in this programming model. To do this, the user has to specify using MapReduce library the 2 functions, the map and reduce function, which we have already explained. Map abstraction is written by the user, which will take the input pairs and produces the set of intermediate key value pairs. This function is to be written based on the applications, and the programmer has to write down as per the application what is to be done in the map function, and the remaining part will take care in the reduce function. So, the reduce library MapReduce library groups together all intermediate values associated with the same intermediate key and passes them to the reduce function. That was the map abstraction. In the reduce function, also it is written by the user, which accepts an intermediate key and a set of values for that particular key. It merges together these values to form a possibly a smaller set of values. Typically, just 0 or 1 output value is produced per reduce invocation. The intermediate values are supplied to the user's reduce function via an iterator. This allows us to handle the list of values that are too large to fit in the memory. So, that means if we see the outcome of the map function, it will generate the intermediate key value pair, which will be taken in the reduce phase as the input. So, here what it does is this stage which is called a shuffle, it merges together shuffle and the combiner. Here there is a combiner. Sometimes combiner is a part of both the activities map and reduce. So, the combiner, so first it will shuffle, that is it will arrange according to the group by keys, and this is called a shuffle, and after that it will combine, that is all the same keys with the values to be combined and is given to the reduce to operate. So, therefore, 0 or 1 output values is produced per reduce invocation. The intermediate values supplied to the user's reduce function via an iterator. Meaning to say that this particular function, which is called iterator, can be understood in more detail like this. For example, if you want to do a summation of the intermediate values, which is basically the sum of its squares. Let us say we want to do this particular summation of all these things. So, iterator has to, for example, if there are maybe another example, iterator has to evolve. For example, if there are iterator has to evolve to see the elements which are similar, it has to scan, and this is called iterator. So, it will scan through all the elements and perform the operation together, and for example, 1 and 4 can be treated together. So, iterator here will identify binary 2 set of elements, first 2 elements, and perform the plus operation, and then it will take the next operation, next element, and perform the plus operation, and then perform then take the next element 16 and perform the plus operation to become the overall sum. So, the iterator job is to scan through this particular list and provide the elements for the operation which is specified in the reduce function. So, we have seen that out of the map function there is a activity which is called a shuffle, which will sort the elements so that all the key values with the same key group by same key, they are to be sorted and given back to the next phase. And in the reduce function, it will use the iterator to scan through this particular list of elements which are already sorted and provided by the shuffle. So, after the map function, lot of internal communication and activities are going on in the form of shuffle and iterator, and then only the reduce function will be applied and give the values out. So, these operations allows us to handle the list of values that are too large to be fit in the memory. And why? Because they are not to be brought at one place, but they are to be operated wherever these values are residing. Hence, it is possible that the operations are performed even on a very large data set which cannot fit into a particular memory. Now, we will just see the structure of the map and reduce function which programmers used to write down, and here we take the example of a word count. We will not go in detail in explanation at this stage. Explanation we will see in more detail in the further slides. So, as far as the map function, this is the pseudocode of a map function. It cannot be executed in this form. Why? Because it has to be programmed as per the specification of that particular language of MapReduce, but we are going to see the pseudocode. So, pseudocode has to specify the map function with the key and value, and where key here in the word count example is the name of the document, and the values are the text of the document which are be retrieved and given in this map function. So, for each word which is basically getting as the value in this particular for each word in the value which is appearing, the map will emit that particular word and 1. Now, the next pseudocode for reduce takes the same format as emitted out of the map function. So, that means the word becomes the key and the value becomes as per the value over here. That format should match, then only the output of map can be acceptable at the reduce function. So, here it is explained that the key is the word and the values is basically the values when it is grouped by key, then the iterator has to operate over this set of values. So, let us take this set of values and we perform the reduce operation. So, reduce will take all these values out of iterator and does the summation and results into that how many times that key is appearing, that is it will do the summation of all the values. So, this has explained the MapReduce paradigm, and let us see some more detail of it. And here we have given the input as a set of key value pairs, and the user has to specify the function map, wherein he has to specify the what is key and what is value, and after that this map function will emit intermediate values in the form of a list which is having a key K1 and V1 is the values. So, K1 and V1 is the intermediate key value pair, and this intermediate key value pair is given to the reduce by the shuffler. So, once the reducer will get the key and intermediate key and value pair, so it will get the entire list of values, and here the iterator will operate on it, and applying the reduce function it will emit that particular value. So, the output will be the K1 and V2 values combined. So, this is the abstraction of MapReduce and overall picture how the program can be written using MapReduce paradigm. Thank you.